Shown in the figure below is a simple yo-yo. The string is wrapped around the outside of the yo-yo, and the yo-yo accelerates downward. A, what is the acceleration of the yo-yo, and B, what is the tension in the string. A yo-yo problem like this is a rotational motion problem because the yo-yo, as it unwinds, will be spinning around its center of mass. And this problem can be addressed by either force methods or by energy methods. Looking at the questions, we can decide which set of methods most directly answers the questions at hand. Since we're asked for acceleration and tension, neither of which appear in the energy equations, we'll be going with force methods. The first step in every force problem is to draw a free body diagram. However, since this object is going to require a torque equation in addition to the force equation, we need to draw an extended free body diagram by drawing a simple representation of the object, which I do by this circle. We then apply forces to our free body diagram, being careful to not only note the amount and direction of each force, but also the location at which the force is applied. We begin with gravity. Gravity is of an amount, mass times g, and it is applied to the center of mass of the object. Secondly, we notice that this yo-yo is attached to a string, and as a result the string will apply a tension force. Tension forces always pull, and looking at the figure itself, we can see that the tension force is attached to the left-hand edge of the object and is pointed upward of an amount t. This free body diagram has one linear dimension. It uses up and down, but not left and right, and will additionally require a torque equation because the object does have an angular acceleration. As always, we orient the plus direction of our coordinate system with the acceleration. In the case of the linear dimension, the positive direction will be downward because the object accelerates down. In the case of the rotational direction, the positive direction will be clockwise because as the yo-yo accelerates, it becomes faster and faster, spinning in the clockwise direction. Let's begin with the vertical equation. The vertical is one of our linear dimensions, and so in a linear dimension we set the sum of the forces equal to mass times acceleration. We've labeled the positive direction as down, and so we get the equation 0.2 times g minus the tension is 0.2 times a. This equation has two unknowns, and so we place a box around it to save it for later. Next, we analyze the clockwise direction. Clockwise is an angular direction, and so as a result, rather than summing the forces equal to ma, we will sum the torques and set that equal to I times alpha. When we look at the free body diagram, we need to determine any one force that leads to a torque in the plus direction. In order for a force to generate a torque, it must be applied away from the axis of rotation and have some component that is perpendicular to the radius connecting the axis to the place where the force is applied. As we examine our free body diagram, we see that gravity applies its force to the center of the object, and so gravity does not apply a torque. Think about that for a moment. If the string were not there, and you dropped the yo-yo, it would not spin on its way down either clockwise or counterclockwise. It is the string that is responsible for spinning the object. And therefore, the tension is the one force that creates a torque in this problem. T is the amount of tension we have, but since we are summing torques, this is insufficient. T is just a force, and in order to make a force into a torque, we need to multiply the force times the radius and take the component perpendicular to the radius vector. Fortunately, our string is already perpendicular to the radius vector, and so this is the entire torque due to the tension. There are no other forces that create torques, and so we set this sum equal to the moment of inertia times the angular acceleration alpha. As you examine this equation, there are two variables in it that you simply don't like. Those variables are I and alpha, and we're going to do something about each one of them. For the moment of inertia, we recognize that the object is a solid cylinder, and we remember that the moment of inertia of a solid cylinder is 1/2 its mass times its radius squared. Secondly, we recognize that since the yo-yo is unrolling off of a string, there's a relationship between the angular acceleration and the linear acceleration. That relationship is that A is equal to r times alpha, so that equivalently alpha can be replaced by A over r. When we make these two substitutions in our equation, it simplifies significantly. The first simplification is that the r underneath of A over r cancels with one of the two r's in the moment of inertia formula, and then the r from the radius due to the torque cancels with the other r from the moment of inertia formula. This leaves us with the much simpler result. Tension is equal to half the mass times the acceleration, which can be further simplified by dividing out the two, leaving us with the equation telling us the tension is equal to 0.1 times the acceleration. Collecting the two equations, we'll be able to solve them out. We notice that just as in the case of linear equations, the principle of the tensions still applies. The tension appears once in the positive direction and a second time in the negative direction. That means the easiest way to solve these equations algebraically is to simply sum them on both sides of the equal sign. On the left-hand side, this leaves only 0.2 times g, and on the right-hand side, 0.1 plus 0.2a is 0.3 times a, leading us to an acceleration which is 2/3 of g, or 6.53 meter per second squared. To finish the problem, we plug this acceleration into either of the two equations in boxes. I'll choose the upper one since it's simpler, leading me to the fact that tension is 1/10 the acceleration, or tension is 0.653 newtons.